All right. Welcome everyone to the second lecture from Mahir Bilen. I would just like to quickly remind you the some of the things about this format. So first of all, we would like to we encourage questions from everybody, especially students who would like to learn more about these topics. The talk will be about an hour long, but again, feel free to ask questions, and at the end, we can continue with the questions even after the recording, if necessary. If there are Turkish students in the audience and they don't want to ask questions in English, so when you're asking, first of all, when you're asking questions, you can just unmute yourself and start asking. You can also use the chat, and I will, if the speaker doesn't notice that, I will just tell that to him that there's a question. And if there are Turkish students who don't want to ask questions in English, they can just type their question in Turkish in chat, and I will translate it and verbally ask the question to the speaker. The meeting is being recorded, and also for written questions, if there's a question that you want to ask by writing on the somewhere, we won't be using Zoom's annotations. We are using Google Jamboard link, and I just put the link on the chat, and so that's about it. So now Mahir Bilen is going to continue with his second lecture for the series.
Thank you, Öztun. I just wanted to ask you before I start whether you got a chance to look at the homework questions or exercises.
But me or personally? Yeah. I mean, I did, yeah.
Me too, but it was hard for me.
I didn't get to all the questions though.
Okay.
The first three was I was able to do it mostly. It was good.
Yeah, I encourage you to please solve those exercises. I think that's really. I mean, of course, I cannot possibly convey all the message that I give in my lectures, but I think they are quite helpful because they will push you to think about the topics. All right, so let me start my lecture. Today, I am going to make an introduction. Once again, can you pin this image so that it would be full screen in your computers? Okay, thank you. Yeah, so I'd like to now from now on, I would like to focus on linear algebraic groups. So remember, a linear algebraic group means that it's an affine algebraic variety, and there is a group structure on that variety, and the multiplication and the inversion operations of the underlying group are algebraic maps, morphisms of the variety. So I'm going to maybe focus mostly on C, but in many places, actually, I will give reference. I'll try to state theorems as broad as possible, but we will be looking at complex algebraic groups mostly. Complex algebraic group means that the underlying variety is a complex algebraic variety. So given a complex algebraic group, a morphism of such an object is nothing but a morphism, I should say, a morphism of complex algebraic groups. Let's say G and H are two such complex algebraic groups. It is nothing but a rational map, which is also a group map. The rational map, which is also a group map, a group homomorphism. here I mean, by rational map, I mean the maps that we can write in coordinates as ratios of two polynomials. Here's a simple example. Consider C star. In the exercises, I asked you to verify that this is an algebraic group, complex algebraic group. In fact, it's algebraic torus, one-dimensional, and this is another algebraic torus, two torus. And consider the map. 1 over z comma z square. So this is a morphism of algebraic groups. Certainly, this is a group homomorphism, and you see it's given by rational maps in the coordinates.
We allow denominator to vanish, like denominator of first one could be z minus 1, right?
Yeah, I could not use that here.
But because there are also those objects, we just look at an algebraic objects without worrying about blowing up anything like this. You know, the field of rational functions. But right now you do worry about denominator being 0, right? You exclude those things.
Yeah, I'm excluding them. They don't. Yeah. So, indeed, correct. Maybe I should also encourage you to, you know, in between these talks, please try to read. I mean, it's a silly thing to say, but please check out some standard algebraic geometry textbooks in between these talks. Just review the basic definitions, like what's an algebraic variety, what's a morphism or map of algebraic varieties, what's a rational map, what's the local ring of a point. Very, very basic objects. They lie at the beginning of the theory. So it would be very helpful if you could review those things by yourself. I mean, the danger is that once I start talking about those notions, the course suddenly may become an algebraic geometry course rather than algebraic group or representation theory class. So please, you would make my life easier if you have a look at it time to time. And I know it is algebraic geometry cannot be learned in 1 week, 1 month, 1 year. It only is developing after you work on it yourself on some research problem. It takes at least 3 to 5 years to digest some of the materials there. So, but sooner you start, better for you, I think. All right. So now, in my yesterday's lecture, I discussed a little bit complete algebraic groups. From now on, I will sort of look into affine algebraic groups. Remember, I mentioned the theorem of Chevalier, which said that any given algebraic group splits essentially. It's a wrong word, but essentially it fits into a short exact sequence where the target is an abelian variety and the kernel is an affine algebraic group. So we will focus on the affine algebraic group word from here on. And now, all right. So few algebraic group terminology that maybe I can quickly tell you. If X is an algebraic variety, I'm always assuming that it's complex and affine. Sorry, I'm not assuming that it's affine. It's just an algebraic variety, not an algebraic group. If X is a complex algebraic variety, then I will denote by OX the structure sheaf of X. This means that if U is an open subset, then this structure sheaf assigns a ring of C algebras to this open subset, and this is simply a set of all rational functions of the form f over g, where f and g are defined on x and g is non-zero on x. Now, sometimes I will simply write OX, and maybe I will omit the subscript x, just write OX. This means that I'm looking at globally defined algebraic functions on x. So these are defined everywhere, so no issues with the denominators. Sometimes these are called global, so this is K or C algebra of global sections. Globally defined regular functions on x. Meaning okay. Now, by the way, I must also tell you that in the standard textbooks like Hartshorne, the underlying assumption for a variety is that they are irreducible. When Hartshorne speaks of a variety, he always assumes that underlying variety is irreducible, meaning that it cannot be written as a union of two closed subsets.
Mahir, in the definition of OXU, the structure sheaf of after that. So there should be U in the definition, right? Maybe Q is non-zero on U or something like that.
On U, yeah, thank you. Yes, correct. Thank you. Yeah, so my assumption is that when I say a variety, let me write to the convention. Our varieties are not necessarily irreducible. The reason for I'm making this assumption or convention is that when we discuss algebraic groups, often they will have connected components. And I just don't want to discard an algebraic group with several components. I don't want to dismiss them as algebraic varieties. I would like to consider their components too. So that's why I'm allowing algebraic varieties to have multiple irreducible components. Now,
sorry, Mahir, could you move the camera a little bit, like to center the picture paper?
Oh, yes.
Oh, okay. All right. Okay, thank you.
Now, another thing that I would like to point out is that let's make this equation. So you see, if I write something like that, OX star, I mean this is the group of multiplicative or multiplicative group of nowhere invertible globally defined regular functions. So in other words, I view my, I look at the the ring of global sections on on X, and I consider its multiplicative semigroup, and then I take its invertible elements. Okay, so these are so this is a multiplicative group with respect to pointwise multiplication of functions. And I'm going to denote this by, certainly constant, non-zero constant functions live in here. So if C star or K star, wherever our field is defined over, K star is a subgroup of OX star. Right? So I'm going to write E of X as the quotient group. This is a very interesting group for our purposes, especially when X is an algebraic group. I'll come to this in a second. But first, I want to discuss a little bit of representation theory terminology. Now, in basic algebra, all of us saw a representation of a group, right? By definition, if G is a group, then a representation, I should say an abstract representation, because this is for arbitrary group, representation of G is a group homomorphism from G to invertible linear operators on some vector space V. Okay, so if this vector space is defined over field little k, then we say that this is a K representation. Standard notation is you either just write the function itself, rho, and call it a K representation, or sometimes you write the pair, rho and V, if G is understood from the context. Now, in this case, occasionally I'll call V to be an S module. A G module. What I would like to point out that in our world, the representation that we are looking at actually requires this homomorphism to be an algebraic group homomorphism. And these are where rho is a morphism of algebraic groups. Okay. Now, so let me give some examples of non-algebraic group representations. So a non-example. So I will write down an algebraic group, but the representation will be non-algebraic. So let's consider the following matrix group, 3 by 3 matrices. These are from our underlying field C. This is a unipotent group. Clearly, U acts on three-dimensional vector space on C by matrix multiplication, but let me insist on the following weird representation. So define so bar means complex conjugate. These are complex conjugates. Okay, so you can check that this indeed defines a representation of U on C3. But because we are using non-polynomial entries, we are taking complex conjugates. This is no longer an algebraic group representation. This is not a rational. When we write down the actual homomorphism rho, the coordinates of that representation matrix will no longer be rational functions because we are taking complex conjugates. Okay, so there is a name for the representations of algebraic groups. They are called rational representations. These are essentially representations where the coordinates of the representation matrix are rational functions in the coordinates of the domain algebraic group. Okay, but I want to consider infinite dimensional vector spaces representations also, and they enter this into this study in a fundamental way. So let me give an example of an infinite dimensional rational representation of an algebraic group. So and then I'll introduce more notation. So GL2 X, for instance, GL2C acts on the polynomial ring and two variables. So if for instance, G inverse is the matrix A, B, C, D, then we get this defines a representation. So if G is like that, then under this representation, the corresponding element of this representation, phi of G, is the essentially takes an element of this ring R, F, and then it gives us AX plus CY bx plus dy. Okay, so still it acts polynomially. Even though this vector space is infinite dimensional, we get a representation that behaves in a way like a finite dimensional representation. And I'll make this a little bit more precise today. Okay, now among all algebraic groups, the reductive groups are the nicest groups as far as representation theory concerned. So I want to introduce some related notation. First, let me define what a simple group is. But first remember from basic algebra, a group is called simple if it has no non-trivial normal subgroups. Right? All of us remember this definition. In the context of algebraic groups, we have to modify this definition slightly. The reason is that connectedness plays a role here, being an irreducible, being a connected group or not. So what we want is essentially this definition, an algebraic group. Is called simple, and some authors call this quasi-simple, but I think simple is fine. It doesn't lead to any confusion. An algebraic group is called simple if it does not contain any connected non-trivial normal subgroups. Okay, so according to this definition, I allow normal subgroups as long as they are disconnected. Right? So what's an example? SLNC, for instance. This you can check that the only in SLNC the only normal subgroups are either trivial group, I should say only non-trivial normal subgroups are the subgroups are the finite subgroups of the center of SLNC. So center of SLNC, by definition, this means that the subgroup that consists of elements that commute with everybody else. Of course, SLNC is a subgroup of GLNC, and we know that in GLNC, the center is just constant diagonal matrices. So SLNC is, the center of SLNC is the intersection of SLNC with the center of GLNC. In particular, we're going to look at the constant diagonal matrices in SLNC. And of course, because of the determinant condition, we're just going to find stuff like that. So this is a cyclic group of order n. So any non-trivial subgroup of cyclic group of order n is a normal subgroup of SLNC. Okay, so now how about a non-example? Obviously, epsilon C cross epsilon C is a non-example. Right, because I can take one of the copies and this is automatically normal in the whole thing. All right. So,
GLNC is also not simple, right?
correct. It's not simple
Yeah, okay.
because, yeah, it is a one-dimensional connected center.
Right.
Now, what about, let's enlarge this definition a little bit more. Semi-simple groups. So these guys are an algebraic group. It's called semi-simple. If it does not contain any closed connected commutative subgroups. Okay, so this time we allow connected, I guess, normal, any closed connected commutative normal subgroups. This time we allow multiple components, as in the non-example that I just wrote, but we don't want them to be commutative. But GLNC is not semi-simple. So semi-simple groups are the ones that we can obtain from simple groups by taking essentially products of simple groups and maybe some finite groups there too. And as far as the tangent space is concerned, by the way, I should point out that even if I take the quotients of these semi-simple groups by their finite subgroups, we'll get the same Lie algebra. So tangent space does not change under quotients by finite groups. Therefore, we can always get rid of center for these objects. Okay, now next I want to talk about reductive groups. Let me give a definition using semi-simple groups. Any group, any algebraic group of the form where G0 is semi-simple, Z is a connected commutative algebraic group, and Z0 is a finite central subgroup of G0 cross Z, is called reductive. Okay, so reductive groups are the ones that we can essentially decompose as a direct product of a semi-simple group and a torus, central torus, up to a finite central quotient. So they behave like semi-simple groups up to a torus factor, this one. Z0 is a finite group, so let's be a little bit not so rigid here, forget about this central Z0, then a reductive group essentially looks like product of a semi-simple group with a torus. Of course, this is not the proper way to introduce a mathematical object. This is actually a theorem. The theorem says that any, more precisely, the theorem says that any connected reductive group can be decomposed this way, where G0 is the commutator subgroup, and Z is the connected center, and Z0 is a finite central subgroup. So what's the proper definition of a reductive group? So to properly define reductive groups, let's start with solvable subgroups. So let G be an affine algebraic group. A subgroup B in G is said to be a Borel subgroup if B is a maximal connected solvable subgroup. Okay. Now let BG denote the set of all Borel subgroups of G. Then certainly intersection of all of these Borel subgroups is a subgroup. Intersection of groups is a group, subgroup. That also intersections of solvable groups are solvable. So this is a solvable subgroup, not necessarily connected anymore. But I'm going to take its connected identity connected component. So this is the connected component of the identity element. Okay. Then I will call this subgroup the solvable radical, or simply the radical of G. This is called the radical of G. Now, it's a solvable group, connected solvable group. Certainly it's normal because if I take the conjugate of a solvable group, it's going to be a solvable subgroup also. Therefore, because I'm using all Borel subgroups, all maximal connected solvable subgroups, this is a normal solvable subgroup. Now, solvable subgroups is from the structure theory of solvable subgroups, I can look at the largest unipotent subgroup of this object. So let RGU denote the maximal unipotent subgroup in RG. Now I'm going to define G as a reductive group. If this unipotent subgroup is trivial. So what's left is then in the radical is just a torus part, because solvable groups, connected algebraic solvable groups nicely decomposes as a semi-direct product of torus and unipotent subgroup. So if I insist on the fact that unipotent subgroup doesn't exist, what's left in the radical is just the torus part. Therefore, when I take my group, if I say that unipotent radical is 0, then I'm left with some toral component. And if I insist that the toral component is also trivial, then it's semi-simple. Just like before. It has no commutative subgroup commutative connected normal subgroup, if I insist on this one. All right, so this is kind of a dry definition of a reductive group. To make things more lively, we need to focus on the representation theory. And indeed, from representation theory viewpoint, reductive groups is the nicest class in the sense that any finite dimensional rational representation of a reductive group decomposes into irreducible sub-representations. The groups having that property are precisely the reductive groups. Okay, so they behave like, in algebra we learned this theorem called Mahir's theorem. It says that any finite group has this property, right? If you take a finite dimensional representation of a finite group, then it always decomposes into irreducible sub-representations. And this class of algebraic groups, so-called reductive groups, have analogous property. Any finite dimensional rational representation of a reductive group decomposes into irreducible sub-representations. Okay, so now I want to go back to the coordinate rings of these objects, okay? Coordinate rings of algebraic groups. So first, I want to define the notion of character. And algebraic, so let G be an algebraic group. An algebraic character of G is an algebraic group homomorphism from G to Gn. So now this is shorthand for multiplicative group of non-zero elements in the underlying field that I'm defining my group over. C star. Okay, so we just take one-dimensional torus, algebraic torus, and look at algebraic group homomorphisms from G to the torus and call the elements, call such homomorphisms characters. Algebraic character. In other words, an algebraic character is a globally defined, nowhere vanishing regular function on G. But we want it to be a homomorphism. So what I call an algebraic character is then fairly close to being so any, in other words, any nowhere vanishing regular function on a group G is fairly close to being an algebraic character. Right? The only thing that I want there is additional requirement is that it has to be a group homomorphism. Now let's remember I introduced this notation E. I want now here EG, which is this. So if I look at these objects, well then this is almost like a collection of characters, almost. Right? Remember this notation. I'm looking at the global regular functions on G, invertible ones, and mod out by K star. So this thing should be fairly close to being a group itself, a character group itself. Indeed, that's the case. This is a theorem of Rosalix.
So by the way, I mean, you might have said this already, but so an algebraic character, I mean, so a character of G is also like a one-dimensional algebraic group representation? Is there a difference?
Well, you can make a representation out of it. Itself, it's just a group homomorphism into a torus, right? To be a representation, it needs to go to, it needs to represent a linear operator. So what you do is you just take a non-zero scalar number and multiply it by the value of the character. Then this defines a one-dimensional representation.
Okay.
Yeah, correct. So now going back to Rosalix theorem, it says that if G is a connected algebraic group, and f is a regular function on G, then f is a character, f is an algebraic character, if and only if its value at the identity element is 1. So this is pretty amazing. This means that up to scaling, so if I pick an arbitrary, or I should take this to be non-zero, of course, invertible element. If I take an arbitrary element in here, and if I scale that function by its value at the identity element, it means that I will get a character. algebraic. So we can catch algebraic characters by looking at the structure sheaf of the underlying algebraic group. It's very nice. Now, so in particular, this is a group. What about the structure of this character group? What kind of group is it, right? It's a very natural question at this point. So there is another theorem of Rosalix. So let's call this one. Second theorem says the following, that X be an irreducible algebraic variety. Then remember EX, I'm not requiring this to be a group anymore, but it's just invertible globally defined regular functions, mod constant invertible global functions. Then this group, it's still a group because it's a group, it is a subgroup, so it's a, and this is a commutative group, of course, or we multiply functions, you know, by their values. They are k star valued functions or k valued functions. So it's under pointwise multiplication. It's a commutative group. Now, the Rosalix theorem says that this is a free abelian group, the finitely generated. Free abelian group. And furthermore, for every algebraic action of G on X, the corresponding canonical action on the global functions this is 3. So it doesn't really act. But the point here is that if you take an algebraic group G here, this theorem automatically tells us that it's going to be a finitely generated free abelian group. It might be, this quotient might be a trivial group, which is still a finitely generated free abelian group. But if it is non-trivial, then it's we know its structure. It's going to be a lattice. Okay. Now, so let's look at some of the examples that we considered before. What about the corresponding group of characters for semi-simple groups? What are the characters of semi-simple groups? So that G be a connected semi-simple algebraic group. Little proposition here. Then E of G is trivial. In other words, semi-simple groups do not have any characters. Any non-trivial algebraic characters. They don't have any non-trivial algebraic characters. And the idea of the proof is straightforward. Just take an algebraic character and then look at the kernel of the character. It's going to be a normal subgroup. And then by simple dimension argument, it turns out that we can focus on simple groups and then take a non-trivial character there. By a simple dimension argument, we see that the character has to be trivial. Proof. Reduce reduce it to the case of simple groups. So okay, so maybe I have to be a little bit more careful here. I want, so you may say that what happens if G is just C star, do we count it as a semi-simple group? Well, technically, it depends on what I call normal subgroup. If I take G to be C star one-dimensional commutative group, then you can argue that it should be called a semi-simple group or not. But if you want to do that, I'm going to assume this dimension of G to be at least one, at least two. I wrote greater than or equal to 2, and I will assign a homework right after this proposition. So reduce the proof to the case of a simple group, and then if chi is a character, is an algebraic character of a simple group, and show that the kernel is equal to G. Okay, so homework. So this is for a little bit more experienced audience. Show that there are no semi-simple groups of dimension 2. So I'm also excluding C star as a semi-simple group. I'm assuming that it's not a semi-simple group. Okay. So no torus is semi-simple. And using that fact, show that there are no semi-simple groups of dimension 2. Okay. Now we know. Yes.
By the way, we have like a few minutes left. Just letting you know.
Okay. Okay. So just like this, we can also show that unipotent groups do not have any characters, non-trivial characters. If G is a unipotent group, then the character group of G is also trivial. So here, by a unipotent group, I mean a group. It's an affine group, an affine algebraic group. Therefore, since it's affine, it has an embedding into some matrix group. So it embeds into some GL of V. So it has a representation V. And under this embedding, the elements of this group can be put into upper triangular form with 1z along the diagonal. Okay, and then just as before, we can show that such a group does not admit any group homomorphism, algebraic group homomorphism into one-dimensional torus. It essentially boils down to the fact that the image of a unipotent element is unipotent, but GM or C star consists of semi-simple elements, and you cannot have a unipotent element semi-simple unless it's the identity. So the only unipotent elements which are also diagonalizable are the identity elements. Okay, so now we saw two classes of algebraic groups that do not have any characters, semi-simple and unipotent guys. How about reductives? Reductive groups have toral parts. They have torus components, therefore they will have a lot of characters. You can certainly write down algebraic group homomorphism from C star to the R to C star. There are many such homomorphisms. Right? In fact, if we look at collection of all algebraic group homomorphisms like that, then it almost behaves like Laurent polynomials, the ring of Laurent polynomials. Now this is now today I felt things were awfully short, so I feel a little what I wanted to say. So today I wanted to actually introduce Picard groups, equivariant Picard groups, and explain their relationship to E of G. There is a natural connection between these objects, but so let me just write down the diagram and stop the lecture for today, unless you want me to continue. But here's a little diagram that summarizes some connections between these character groups and the geometry of line bundles on some varieties. Okay, so this is a proposition, or I should call it a theorem, by Knopp, Luna, Bush. So let G be a reductive group. And let X be an irreducible G variety that admits a quotient so Gx on X, and we are assuming that the quotient of X by G is a variety in very, very loose terms. Then we have the following diagram, commutative diagram. And we have the following diagram whose rows and columns are exact. So it starts with the trivial group, and we look at the E of quotient variety. This injects, this is a subgroup of the G invariance in E of X. Of course, as I pointed out before in the previous proposition, if G is connected, then the section is trivial. So this will be E of X automatically. This also goes into E of G. So we are now looking at the character group of G. And then we have the group of algebraic cycles on G with values on this sheaf. And then we have this finite group now we look at the H1 of the E of X on this finite group. And on this side, we have the equivariant Picard group of X, whatever that means. I will verbally explain it. And then we have the Picard group of X. And in here, we have Picard group of the quotient variety. And this goes into a product. These are the character groups of the stabilizers of certain points of the variety X that comes from the closed orbits of the G in X. So this diagram, so what do I mean by PIC? Here, PIC is the group of isomorphism classes of line bundles on X. The group of isomorphism classes. So elements are isomorphism classes. And for a line bundle, we can talk about whether it is linearizable with respect to G action or not. So this means whether it sort of has some representation theory content or not. So the G linearizable line bundles is denoted by PIC G of X. And so these guys fit into each other this way. Now, from this diagram, one obtains some really nice corollaries. For example, sometimes one can conclude that PIC of G mod H, if X is G, if G is a if X is a quotient homogeneous space viewed as a G variety, by diagram tracing, we can sometimes show that this is actually the character group of H. So the point that I wanted to make by presenting this theorem today was that the character groups of algebraic groups and the multiplicative groups of globally defined regular functions actually give direct information about the geometry of the homogeneous spaces that we consider. So line bundles on homogeneous spaces are essentially closely related to characters of the underlying the group that we are quotienting with. And so now I know I'm over time. I'm trying to now do some damage control. So the lecture is sort of finished rather quickly. Now I probably should continue. It's a bit. I'm a little bit frustrated because I still have some nice stuff to show, but at the same time, tomorrow I want to move to a new topic. But it is what it is. Maybe we will have more lectures like that.
Yeah, hopefully this will make you teach us more, in the future as well. I mean, on top of the lectures for the rest of the week.
You stated this theorem of exact sequences.
Yes.
You feel bad if you don't see why these things are exact.
We should see why they are exact.
No, I mean, you didn't prove this theorem, right? You mentioned.
No, I was only able to state it. Yeah, I couldn't prove it.
Yeah.
So proving rigorously would take at least one lecture by itself. I was going to drive some consequences of this, and there are some nice simple consequences as I was writing there. For instance, the character group, if you look at the homogeneous space, the character group of G maps into character group of the subgroup, and then that maps into Picard group of the quotient, and then that gets into the Picard group of G. So there are these very nice consequences, like it just falls out of this diagram.
It would be nice just to have a feeling why this thing is exact. But at least we would have, how to proceed is seeing this exactness from the statement.
Yeah. But the proof is going to take a long time. Explaining that, showing that they are exact is actually proving the theorem, right? It's
by the way, I'm going to stop live streaming and recording so we can continue to chat.
Okay.